So welcome. In this video we're going to cover part of chapter 15.1 and 15.2, specifically dealing with how water vapor gets into the atmosphere and some of the ways that we measure water vapor in Earth's atmosphere. So starting off with chapter 15.1, I'm going to skip the beginnings of that section and really go into the very last bit of chapter 15.1 that talks about how water vapor enters and leaves the atmosphere near any body of water's surface. So basically what the three images are getting at is that you have water vapor in the atmosphere, all throughout the atmosphere, but near to any body of water, there's an exchange of molecules between that body of water, liquid, H2O. There's an exchange of material between the liquid water, so a little bit of the liquid water is evaporating, and some of that water vapor is returning back to liquid water. And this is something that's constantly going on, no matter the given temperature. And the three scenarios that are given are equilibrium, if there's an energy increase into the system. In other words, if there's a thermal increase, if the temperatures are rising, or if the temperatures are falling. So if there's no change in temperature, eventually this parcel of air directly above the water will reach a state of equilibrium. If the H2O leaving water equals the H2O entering water. So this happens because all of the molecules, both in the atmosphere and within the water, have energy. They're moving around. In the atmosphere, those molecules have even more energy than they do in the water, which is one of the properties of the water being a gas phase, having more energy. But there are some molecules that have kind of this borderline energy where they could be in a liquid or a solid state. And this occurs both in the atmosphere as well as the liquid water form. And so it's these molecules that have energy states that kind of overlap between an atmospheric and a liquid state, a gaseous versus a liquid state, that these molecules are the ones constantly being exchanged. So we're only at equilibrium if there's no energy increase or decrease. If there's an energy increase into the system, then more H2O leaves compared, more H2O leaves compared to H2O entering water. And we get a net evaporation, if you will. If there is an energy decrease, there's an overall system temperature decrease as well, and H2O enters water greater than H2O leaving water. So you can write that a variety of ways. So I really introduced this portion of chapter 15.1, not because the rest of the chapter of the section is unimportant, But because it goes right along with what I wanted to talk about, which is 15.2. So make sure that you do understand the rest of 15.1. But moving on to section 15.2, in terms of what is humidity, we need to talk about humidity and vapor pressure first. We'll get to humidity in just a second because we have two different types, but I've already used a term, vapor pressure. Vapor pressure is the amount of air pressure exhibited just by water vapor. So many of you are familiar with air pressure. Air pressure is measured a variety of ways, and one way would be a millibar, just like a milliliter, 1,000th of a liter, 1,000th of a bar. But this is a pressure term instead of a volumetric term. Air pressure is actually the sum of all of the different gas molecule phases. So H2O pressure plus O2 pressure plus nitrogen pressure, etc. If you were to take a chemistry class, you'd learn that air pressure is a summation of all of the different gas pressures. And so with respect to vapor pressure, we're talking about water vapor pressure. And if there are more water molecules in a parcel of air, then the water pressure is higher. If there are less water molecules within a parcel of air, then there is a lower vapor pressure. So we experience vapor pressure most directly whenever we talk about relative humidity. Certainly this time of year, the Houston, Pearland area, Clear Lake area is extremely humid all day. But if you were to look at a chart, such as going on darksky.net, my favorite weather app, you can see how humidity levels change throughout the day. And you'll notice, and runners are very aware, that early morning is a time when humidity levels are the highest, and late afternoon are times when humidity levels tend to be the lowest. So we're going to talk about what this term humidity means, and you can also go on weather apps such as Dark Sky and read something about the dew point. And that's another term, but if you were to look at dew point values throughout a particular day, in most cases, this value doesn't change too much. It might change by 1 or 2 degrees. We refer to dew point in terms of a temperature, and so those temperatures don't change too much for dew point, whereas humidity levels do change. So this is all going to be based off of a graph, and you can see the actual textbook graphs in chapter 15.2 at the bottom. And on the left-hand side, on the y-axis, we have vapor pressure, and on the x-axis, we have temperature, with temperature increasing that direction and vapor pressure increasing that direction. And there's a curve plotted. That's called the water vapor capacity. Basically, if you plot above and to the left of that line, any air that has a vapor pressure and temperature that plots in this field right here is super saturated with water pressure, or with vapor pressure, with water vapor as a gaseous phase. This is not a typical scenario that takes place. Typically, fluids, including gases, do not become supersaturated in a substance, at least not for a long period of time. That curve right there is water vapor capacity. That is the saturation line. So, any temperature associated with a water vapor pressure that would plot on this line would be completely saturated, meaning air cannot hold any more water vapor than is already being held. We can write that down. No more H2O vapor than this under normal circumstances. So down here, we are unsaturated. Okay, so how do we deal with and read this graph? A couple of ways. Any given day has a temperature value, say 73 degrees. Let's actually use this morning. Actually, this morning's not good because we'd be plotting really close to the line. Let's say we live somewhere nice like Denver, and it's 60 degrees in the morning. So here's your 60 degrees. "60 degrees is associated with that vertical dashed line. Say the vapor pressure is, I don't know, 25 millibars, associated with 25 millibars. This is not going to be drawn to scale. So if I were to plot 25 millibars of H2O pressure in Denver this morning, temperature and pressure would plot right here. Okay. Typically, what's reported is humidity. And anytime you look at a weather app, typically you're looking at relative humidity and dew point. What are these two numbers? Humidity is a ratio of the total amount of water vapor that can be held compared with the amount of water vapor present. So relative humidity is equal to the present divided by the total compared with these two numbers. And it's a percentage, so in this case it looks like it might be around 40%. So this is why humidity is given in terms of a percentage. If we take Houston, for example, or Pearland this morning, I'm not going to label the axes are the same as the previous slide. I'll bring that back. Pressure. I might as well. Here's the curve again. And say in Houston, it was 79 degrees. Humidity this morning at the time that I ran in Pearland was 99% humidity. Well, that means the vapor pressure was right up here because, again, the present divided by the total. Notice that the dot is almost all the way to the saturation curve. Okay? So we have two scenarios. We have Denver, whose humidity was 40% this morning, and we have Pearland, whose humidity was 99% this morning. But we have another metric, the dew point. The dew point is the temperature at a given air pressure at which the air would be saturated with water. So we can saturate a parcel of air one of two ways. We can either increase the vapor pressure, or we can decrease the temperature. The dew point is the temperature using the graph moving directly to the left, the temperature at which a specific air pressure becomes saturated in water. So 40 degrees. Let's use a different number, 35 degrees. Say that's 35 degrees so that we're not confusing it with relative humidity. So the dew point would be 35 degrees. Okay, let's go back to Houston and Pearland. Pearland had a humidity of 99%. That was because that was a ratio of the vapor pressure divided by the total amount of vapor pressure that temperature could hold. But what's the dew point? Maybe 78.5 degrees? Because of the same thing. Remember, we went to the left until we encountered the line. In this case, we go left to encounter the line, and we didn't have to go too far. 78.5 degrees maybe. I'm making these numbers up, but I'm showing you the basic techniques that you would use. Now, I mentioned if you were to look at a dark sky app at darksky.net, and you were to look at humidity, we can talk about some of the patterns that you can look at throughout the day. A typical day consists of, here's 7 a.m., noon, here's 7 p.m. A typical day has an increase in humidity and then a decrease in humidity and then back up. An increase in humidity and then a decrease in humidity. Whereas the dew point stays the same. Typically, unless if a new air mass moves in. the dew point tends to not fluctuate a lot. So why is it that the humidity fluctuates but the dew point stays the same? Well, it has to do with temperature changes throughout the day. At 7 a.m., temperatures are the lowest that they are. But as the day progresses, temperatures increase, causing humidity to decrease until after sunset, temperatures start to decrease again. Because let's look at this. Let's do another scenario. Say it's early morning and humidity is equal to 99%. That's 99% of the total line to the curve. And that's associated with a certain temperature. So that's early morning. As the day progresses, temperatures increase. Temperature at the heat of the day is over here. The temperature increases on this axis. The vapor pressure didn't change. The temperature did. So now we're plotting right here. Now the humidity may be only 50%. So we start off with a humidity of 99% in the morning. Vapor pressure stays the same as the temperatures heat up as the days progress, and